Hello, everyone. Thank you for joining. Um, so I hope everyone is doing fine and their health is good. So yeah, I have already introduced myself in the GRB channel, but I'll do it again. My name is Hardik Medi. I'm currently a second year BSc student at River University. So with me, I'll be the guide in this project, and with me, Ashwin.
Hey, am I audible?
Yeah. Am I audible? Hello.
Hello?
Yes,
Hello. Am
Hardik,
I?
you are. And also Vikrant, both are audible.
Okay. Cool. Okay. So I, Ashwin, and Sasi will be the guides for this project, and Vikrant will be our mentor. So uh, please introduce yourselves. I would like to know everyone over here. So just tell me your name, your college, and where are you from? Yeah.
Hello,
Hi.
I'm Anuru and I'm from Calicut.
Okay.
I'm a student at National Institute of Technology, Calicut, third year
Okay.
engineering physics. Nice to meet you all.
Hi,
Looking
nice to meet
forward to
you.
working with you.
Same here. Same here. Thank you for joining. Others?
Hello.
Hi.
Yeah, am I audible?
Yeah.
Yeah, so I am Saitesh Amonkar and I study in St. Joseph's College, Bengaluru, BSc second year, and I am from Goa.
Okay. Which section are you in?
PM.
Okay. Thank you for joining.
Hello,
Hi.
I'm Jyotika. Right now third year integrated physics, and I'm from Amriteshwari PM Coimbatore campus. And I hope this research project will give a lot more basic ideas to improve myself.
Okay. Thank you.
Hello,
Hi.
I am Manjima. I'm from Kannur district, Kerala. I'm doing my third year integrated physics in Amrita University, Coimbatore campus.
Hello,
Hi.
I'm Rizal, first year student at Punjab Engineering College, Chandigarh.
Okay. Thank you.
Hello everyone,
Hi.
I'm Ayush Sonare. I'm from Pimpri Institute College of Engineering, Pune, and right now I'm in Nagpur.
Hi everyone, my name is Tanay. I'm third year electronics and telecom student, engineering student from DJ Sangvi, Mumbai.
Hello.
Hi.
My name is Kshitija Chirsagar. I have just completed my MSc in Physics from Institute of Science Nagpur. And I have also done the lattice course with you guys, and that was very awesome. I enjoyed it very much. So I'm looking forward for this course. Thank you very much.
Thank you for joining again. Hello. Your voice is breaking. Hello. Stephen, your voice is breaking. I'm sorry, your voice is breaking.
Yeah, I think there's some network disturbance.
Yeah.
Hello.
Hello.
Hi.
Yeah.
Irfan.
Good evening to everyone. My name is Mohammad Irfan. I am from Srinidhi Institute of Science and Technology, Telangana. I'm actually pursuing my mechanical engineering. I'm in third year currently. Looking forward to work with you all for this Gamma Ray project.
Same here. Thank you. I think Akshara was speaking.
Yeah. Hi everyone. I'm Akshara Rathod from Hyderabad, and I've just completed my BTech in Electronics and Communications Engineering from NIT Nagpur. And I'm new to the field of astronomy, and I'm really very excited to explore about it. I'm really looking forward to learn from each one of you. Thank you.
Thank you.
Hi everyone, I'm Rajat and currently I'm pursuing masters from Sridev Suman University in Uttarakhand, and currently I'm in first semester. This is my very first project that I'll be working on. So in graduation, like I haven't really got much of exposure to these projects and all. So I'm looking forward to working on this one with you guys. Yeah, thank you.
Thank you.
Hi, I'm Suhana. I'm
Hi.
from I'm a second year grad student from SJC, and I'm from Bangalore. And this is my first project ever, so I'm looking forward to it.
Hello, this is Anushka, and I'm doing my BSc in St. Joseph's College, Bangalore, in Math, Statistics, and Economics.
Oh, nice. Which year are you in?
Oh, I'm in second year.
Okay. Thank you very much.
Welcome.
Hi, I'm Shivalik. I'm a third year BSc student at St. Joseph's College, and I'm from Bangalore.
Good.
Hi everyone, I am Lalita from Srinidhi Institute of Science and Technology, and I'm studying in mechanical engineering, and I'm second year. Nice to meet you all.
Nice to meet you as well.
Hi everyone, I'm Muruhappan, doing aeronautical engineering first year in Anna University, and I'm looking forward to this. Thank you.
Thank you for joining.
Hi, this is Seth. I'm from Reva University, studying second year BSc from Andhra Pradesh.
Thank you for joining, Sharat.
Hello everyone, myself Alan Sebastian. I'm coming from St. Stephen's College, DU, and I'm looking forward to work with you all in the future. So excited. Thank you.
Same here. Thank you for joining.
Yeah, can you hear me? Hello?
Yeah.
Hi everyone.
Okay, my name is Hariprasad. I am from St. Stephen's College, Delhi, pursuing my first year BSc Physics Honors. I'm actually from Kerala, but I am studying in Delhi right now, studying in St. Stephen's College right now, and I'm really excited for this project upcoming weeks with all of you guys. Thank you.
Good. Thank you.
Hi everyone, this is Prakti. I'm currently in my third year of electronics engineering from AKTU Lucknow. I'm very interested in physics and I am extremely excited to get started with this course and learn new things. Thank you.
Hi everyone, I'm Vedant. I'm a first year student at St. Stephen's College, Delhi, physics honor. And yeah, I'm really interested in astronomy, data analysis, and stellar dynamics. So I'm really looking forward to that.
Thank you for joining.
Hello, my name is Vaishak. I'm the final year of BTech in Engineering Physics, and I'm from Kerala.
Hello, my name is Sumedha Rao. I'm currently pursuing mechanical engineering third year from Pune, and glad to meet you all and looking forward to this project. Thank you.
Thank you for joining.
Good evening, everyone. I'm Rohan Singh. I'm currently studying BSc Honors Physics first year from St. Stephen's College and looking forward to work with you all. Thank you.
Thank you.
Hello, my name is Pranaz Kazi. I'm from Kolkata. I'm currently pursuing engineering third year from Techno International. Really excited to be here.
Thank you for joining.
Hello everyone.
Hi.
My name is Divyansh. I am from St. Stephen's College. I'm in first year physics student. It's very nice to be here.
Thank you.
Hello everyone.
Hi.
I'm Sejal, but I go by Alice, and I'm pursuing BTech in Production and Industrial Engineering from NIT KTR. I'll be entering my third year this fall if everything goes well with one particular course. So I'm also interested in robotics and its application in space exploration, and I'm looking forward to working with you.
Thank you for joining.
Hello.
Hi.
Hello, everyone. Yeah, I'm Atul Kulkarni. I have completed my mechanical engineering, like my bachelor's, and in year 2019. And right now, I'm like waiting for the JAM counseling and about to enter in a MSc Physics degree. And I'm from Khargone district, Madhya Pradesh.
Nice to have you here.
Yeah.
I think that's all right. Yeah. So no one here is from school level, high school level.
Hello.
Hi.
Am I audible?
Yeah.
I'm Pushkar, and I'm a native from Lucknow, but I'm pursuing my first year from Hansraj College, Delhi University. Actually, I find the aesthetics and physics very fascinating, and so I'm looking forward to do research in my future. And so it is not often that we get an opportunity to express ourselves with our peers who are interested in the same kind of things, and so this project. Thank you for giving this opportunity. Looking forward to interact with you all.
Thank you for joining. Okay. Is anyone left? Okay, I think that's over. So, well, this is a 6-week course, so I'm sure we'll have more time to interact and we'll get to know each other better. So, please, just a reminder, please fill this form. Only like 25 people have filled it. So please fill this form. Again, it will help us get to know you better, and also for selection for a solar project will also occur from here itself. So please fill it. Okay. So just a brief overview of the grading system that we'll be following. Each entire project is for 1500 grade points and 250 grade points for each week. You can see the weekly overview, weekly activity division over here. So you'll be having assignments. Assignments as in basically you will have a write-up. You have to write an article kind of thing. So that will be for 50 grade points, and weekly review. This weekly review will help you write your research of academic article at the end. So this will also help you keep track of what you learn each week, and will be grateful. Will be helpful for revision in your future project endeavors. And then there will be a quiz each week. So there will be 10 questions, 1 grade point each. And just to make it a little bit similar, we'll be scaling up the total marks to for 100 marks. So like if you get 6 out of 10, then your points will be up to 60. Just note that your final certificate will not contain your total grade points. This is not in traditional education system, so there will be no judging based on your points, but just to create a little bit of incentive and to create a little bit of excitement, we have introduced this grading system and leveling system, which will be in your certificate. So I just named it a little bit of like interesting names. So that's the grade points, 0 to 500, 500 to 1000, and 1000 to 500. So again, the final goal of this project is to gain experience and to learn new stuff. So even if you don't score well, doesn't matter. Everything we do at Naxxatra is to gain experience and have fun. Yeah, so I'll be uploading this PPT in the LMS also, so you can have a review of the grading systems later on. And if you have any go downs, please ask us. Okay, so as you know, we'll be having 6 weeks of course, and so this week is week 0. Week 0 is basically preliminaries. So we'll be covering the basics of vector calculus, Maxwell's equations, and Python pandas package. So what's the purpose? Basically, see here we have some students who are not familiar with such concepts, so they'll be introduced to it, not in detail, but at least an introduction is more than enough, so they can carry on later. and also for veteran students, for high level students, for MSc or fourth year, third year, it'll be a revision. So everyone wins here, and it's a win-win situation. Okay, so this is week 0 breakdown. I've uploaded a daily breakdown in the server, I mean channel. So each week you'll be getting the breakdown and the resources list for that week, so you can go through them just in advance. It'll help you understand the concepts. And so as I've told, the weekly will be assignments, weekly will be and quiz. So this week these 3 will be there, and so article writing and this is the topic. Basically, the details will be shared on Wednesday, so don't worry about it now. I'm just giving you a heads up. So if you want to, you can read on the advantages and disadvantages of EM waves astronomical messengers. So we know as there are like 4 kinds of astronomical messengers: electromagnetic radiation, cosmic rays, neutrinos, and then gravitational waves. So the summer project here in multi-messenger astronomy is divided into 2. EM waves and neutrinos. So neutrinos is the other project, and this is for the EM waves. Mainly, we'll be focusing on GRBs, as in that's gamma ray bursts, because gamma rays are the highest, highest energy in the entire EM spectrum. So it's much easier to study them. There'll be a quiz. The quiz will be based on the questions of the concepts that are taught, discussed that week. So this week, since we'll be discussing vector calculus, Maxwell's equations, and Python, so the quiz will be based on that. It'll go live on Saturday, each Saturday, and you'll get like around 1 day to submit it. And you'll also have to submit a weekly review by the end of the week. So yeah, just keep some note points if you want to. Again, I'll be sharing this PPT. So okay, so is there any doubts, or do you have any doubts? I think we can clear some doubts here right now.
Hello.
Hi.
Yeah, I have a actually doubt regarding that general information form. Actually, it includes you have to like select the point if you are in undergraduate or postgraduate. But as I told you, I'm right now I have completed my BTech in 2019. So what should I select? Like I'm not currently enrolled in any of the program. So
okay, no, that's fine. Just select postgraduate. This doesn't matter actually. All we want is to get to know you better and your coding skills. So it's fine.
Okay.
Yeah. Any more doubts?
I want to ask, do we have to write an article of whatever we have studied in the week? Not an article, at the end of every week?
Right, so that's for a weekly review. So whatever you learn that week, you can make points. You can either write in Word, or if you know LaTeX, you can also write that in that. And so aside from that, there'll be like a small article based on a small topic, so that it'll help you start your own self-study, because this is a project, right? So not a lecture series, so it'll be heavily self-study based. And so these articles and quizzes will help you start your study writing. So articles will have a small topic, and weekly review will be based on what you have learned that week. I hope that's clear. Hello.
Yes.
Am I audible?
Yes.
Okay. So whoever was asking the doubt, I hope it's clear now. Any more doubts? Please feel free. Okay.
Hardik, maybe you can tell them a little about what this project is all about.
Right. Okay.
Before we get into the vector calculus thing. Reason being, we might expect a few people from the neutrino group to join in for vector calculus. So just give them a brief about what this project is all about and what is it that they should expect out of it, and how are they expected to work and so on.
Okay. So this project is to introduce you to the concept of MMA, multi-machine astronomy, and to get you started on the research, paper reading process and writing articles. And so by the end of this project, you'll be able to write articles and have a much better understanding of the MMA. And also we'll be dividing the groups later on, and like in the end of week 2. So each group will be having a specific problem statement that will be discussed later, so not now. For now, we'll be just for the first 2 weeks we'll be covering the basics, since you see math is a language of physics, right? So this will be covering a few of the basic concepts this week, and then next week we'll be covering the basics of supernovae and all the related stuff. So I'll be posting all this stuff in the channel and in the LMS website. So yeah.
Okay. So today we're supposed to work on vector calculus, basics of vector calculus. But before we get into that, I'd like to know your opinions of what would you expect out of these 6 weeks project, right? I mean, many of you have told that this is kind of your first time working with an actual project and so on. So what are your expectations, and what are you looking to take away at the end of 6 weeks? Can we have like a few people unmute and let us know about that? And you might have already realized, I'm just trying to stall here so that just so that we can see if anyone from the neutrino group joins in, before we start off with the vector calculus thing. So yeah, can someone unmute and let us know about what their expectations are of this project?
Hello.
Hey, go ahead, Atul.
Yeah, I think after this period of 6 weeks, at least we'll be having two things in our hand: a peer group, and with whom we can share and like understand the different topics. And the second thing, that we don't have the habit to read research paper or everything until and unless we have the requirement. So I think this will at least instill an habit in us. So yeah.
That's a very good way to look at it. I like the part where you talked about you getting a peer group. So that's nice. Okay, so I don't quite remember Stephen's real name, so I'm just going to go ahead and tell Stephen from the chat box that yes, they do have a discussion going on, but it's not that important, as in they're just discussing doubts and stuff. You won't really be missing out on quite a lot. The content for today is more or less done with the neutrino group, so you don't have to worry about it. Okay, so coming back to that, can someone else let us know what expectations they have?
Yeah. Hey, so as I said, this
Hey,
will
Rajat.
be first project. So there is a lot that goes on into writing a particular academic writing. So
Right.
at the end of the project, I am hoping that I'll get to know all the prerequisites, right? How do we collaborate with other peers? How do we read the research papers? How do we go about writing the stuff, basically organizing our thoughts, all that? So this is a great introduction for me, because being a first project. So, and after this, I'm looking forward to go deeper into the research work, and also that by the end of my masters I can at least write a decent review paper.
That's really nice. So one point that you brought up here is about the notes, and one thing I'd like to mention, because electromagnetic stuff, electromagnetism as a whole, not just looking at gamma rays but the entire spectrum, is highly mathematical, right? As most of you would have already have a rough idea about Maxwell's equations and so on. It is highly advised that you make daily notes of everything that you learn, and not just during these sessions, but even when you're doing your self-study apart out of these sessions, or any research paper that you read, any textbooks that you read, any paragraph or any section. It is advised that you make notes out of it, so that it doesn't only help you over these 6 weeks, but you have them ready for whenever you need them in your future. So even if you're going ahead and doing a project on say gamma ray bursts, you don't have to go through the entire basics all over again, because you'd have these notes ready with you, right? So starting today, since we'll be dealing with vector calculus, you can start taking notes and stuff. I will not be, I mean, any sessions that you have of mine, Vikrant, I won't be doing them in depth. Reason being, I sort of appreciate self-study a lot more than someone teaching it to you, because all of us here are accustomed now to the whole regime of online classes, and you have some random person, your teachers basically, teaching it to you on a screen. They're just writing or showing a presentation, and then you're just listening to them. It gets monotonous. It gets boring. Is there anyone who disagrees with me here? You can say yes or no. Is there someone who disagrees and finds online classes very interesting?
Not at all.
Right. So yeah, so that is the last thing that I want to make this. Do not think of this as just any other online class or online session, but I want you to look at this as sort of a discussion group, like most of you mentioned it being a peer group, and you get to meet people with the same mindsets, people who you can discuss with and explore ideas. Make sure that you do not look at this from a classroom perspective. Even though the server is named Classroom Plus Plus, we want it to be a collaborative classroom where there are no boundaries at all. So you are free to go into the neutrinos group meeting and see what they're doing out there. And like today's, the neutrino people are welcome here, right? To see what's going on in the electromagnetic group. And fairly speaking, multi-messenger astronomy as a whole deals with all of these in combination, right? If you pick any supernovae, for example, I think the most famous example is the one in the Large Magellanic Cloud called the SN 1987A. This is one supernovae that has been known to emit all known forms of multi-messenger stuff, right? Electromagnetic radiation, yes, obviously, because that's how you see it. That's how you visually see it. It's also predicted to emit neutrinos and also predicted to emit gravitational waves. And that's something amazing, because you just have one body and it's emitting the 3 of the 4 multi-messenger stuff. So studying just that one single thing will give you all the information you need. Similarly, this entire project, the so-called project on multi-messenger astronomy, I want you to look at this as an opportunity to learn different things from different places, and not just restrict yourself to what's going on in these sessions or the references that you are given. So yeah, I think I've ranted quite a lot. Is there anyone here in the participants list from the neutrino group? Can you maybe raise your hand or click yes or whatever option you have on your version of Zoom? All right, so we seem to have a few people. Okay, yeah, Stephen, I know about you. Thank you. Okay, we have Anshul. All right. Maybe you can just put a yes in the chat box if you're from the neutrino group, so that if there are enough people, we can get started on vector calculus, basic vector calculus. Okay, we have around 4 people so far. No problem, that's okay. Are you guys okay with a little bit extension of time? I know we mentioned it's gonna be up till 8:30, but are you guys okay with a little bit of extension, depending on how things go on? Okay, nice. So about the doubts and stuff, I would rather keep it. You keep it until the end of the session, so that I can finish whatever it is that I'm doing. Because I don't want to extend it too long, right? It's a Monday night and everyone has had an exhausting day already, and extending it to dinner time is a little bit of a drag. Right. So I'm gonna get started. Let me just set things up. All right, I'm gonna share my screen. So Hardik, can you please let me know if you can see my screen?
Yeah.
I'm gonna get rid of Telegram for a while. Alright, please let me know if you can my
Yeah, wait. I think it's a my network issue. So can someone else confirm? Is the screen visible?
No, it's not visible.
Yeah, now it's visible.
Okay. Vikrant, I can't hear you. Hello. Can you guys hear me?
Yeah.
we can hear you.
Okay, so I think he has some information. Vikrant. Vikrant, your voice is breaking. Can't hear anything.
audible?
Hello. Yeah. Voice is still not clear.
Can you?
Vikrant, are you on Geo? Can you please move to Geo? Okay.
Okay, so he has some network issues. So could you guys, like, I didn't ask that time because I thought we wouldn't have much time. So now, and as now, could you guys like talk about your previous project experience that you have worked with?
Hey, can you hear me now?
Yeah.
Okay, I've joined from my phone.
But it's echoing though.
Yeah, now?
Yeah.
Okay. Can you give me sharing rights? There's two of me. I'm on my phone and on my computer.
Okay,
You
I'm
just
making
give
a co-host.
us the co-host.
Yeah, I made a co-host. Just check now.
No, the other one. We'll have to make the other one co-host. The one without the picture.
Oh, okay. Yeah, done. Check now.
I don't see it yet.
Yeah, I made you both Vikrant Pulamati.
Really?
Yeah.
No.
If you have something to share, just send it over to Hardik and let him share the screen.
No, I'm gonna write it. So just a moment. If it doesn't work out, then I'm afraid we'll have to move it to tomorrow. Let me just try one last time. If it doesn't, then I'm afraid we'll have to move it tomorrow. It wasn't giving an issue till now. I don't know. Meanwhile, you guys can keep talking while I try to figure this out.
Please talk about your previous projects.
Yeah, I think at least 10 of you had filled the form who mentioned that you worked with something before and a couple of other projects. So just feel free to unmute and talk about it.
I think Shivalik, you can talk. You have a lot of experience, right? So, are you here?
It's not a lot of experience, but
oh come on! I saw your form.
Yeah, but it's more of learning how to do things than doing the things. But yeah, so I worked with some Gaia data to sort of plot a HR diagram and light curves and try to get redshifts and all from the spectra and calculate distances and all of the basic astronomy stuff. I haven't done anything quite in depth yet. So this will kind of be the first one.
Okay, that's interesting.
If there's anyone from the Safied's group who kind of did a couple of the first tasks, you can just talk about that. If there's anyone here from Naxxatra's previous Safied group. I think Vijay.
Yeah, hello.
Hi.
Yeah, so I was in the survey group. There what we did was we actually collected data from actually identified sapphires, and we studied about the period luminosity relationship between them, and we had a set of fits files in the sense we have set of images of an unidentified sapphire, and we needed to calculate the period and the distance using the data we collected before. So that was one thing I did. I had some few other works too with gravitational lensing and everything. I have collected data from something called Slack survey. Slack survey that they collect details for gravitational lenses. So I squared out data from there, and I had to estimate the Einstein ring radius and everything. That's it, basically.
Okay, anybody else wants to share? And Vikrant, any luck so far with sharing your screen?
Yeah, no, I don't know. It hasn't been working at all. It's not detecting me on my computer for some reason.
Okay. Maybe you can just shut off the computer and turn it on again. Otherwise, if you want to share while sharing a note that's already there or a PDF, that can be done now. But if you want to write, then we'll have to move forward.
Yeah, I think we can work with the electrodynamics book if one of them
Hardik
can.
had put a vector calculus resource on the LMS.
I think I can share my screen. Just hold on. I think I got the access now. Let me know if you can see my screen. Yes.
Yeah.
So I'm gonna try writing, and you just let me know. Yeah, it's
perfect.
Brilliant. Awesome. Really sorry about the entire delay that happened. All right. So we're going to get started off without further ado. I'm assuming that everyone here already has a basic knowledge of vectors until at least cross product. But we'll quickly go over the basics again. And you just let me know if there's any breakage in my voice or something. All right. Okay. So if you have, let's say, two vectors, A with components AX, AY, and AZ, and you have two vectors, you have another vector B, BX, BY, and BZ, then a dot product between them is defined, dot product. This is also called an inner product or a scalar product in 3 dimensions. I'm going to stick to only 3 dimensions right now of space. That is defined as A dot B, hence the dot. And it's again defined as magnitude of A, magnitude of B times the cosine of the angle between them. The next is, of course, the vector product or the cross product. This is defined as A cross B with a cross symbol there. And in 3 dimensions in our regular Cartesian system, it is defined as the determinant of these 3 rows, which is here we have the components of A, AX, AY, AZ, BX, BY, and BZ. This would give you the cross product between both of them. And if you want to get into a trigonometric or a projection type definition of a cross product, then it's the same as magnitude of A, magnitude of B, sine of the angle between them times an n cap. This n cap is a vector or a unit vector with magnitude 1 perpendicular to the plane with A and B. So if you have, let's say, a plane where you have A like this and B like this, then your A cross B is going to be pointing perpendicular to that. This is going to be A cross B. So that's just about cross products. The next, of course, you can extend this idea to triple products. It's called the vector triple product. It's the same way you define anything, but it's a little slightly different in its implications. So you write it as A dot B cross C. So the component wise, it's just AX, AY, AZ, BX, BY, BZ, and CX, CY, CZ. What this just gives you is a number, a scalar, which is equal to the volume, or 6 times the volume, but I'm going to ignore the constant, of a parallelepiped. If you're familiar with this, then it's great. If you're not, don't worry about it. It's nothing important. I'm sure all of you are already aware of the displacement vector. So in a Cartesian system, or in any system for that matter, if you have a reference point and you have a point where you need to find out, where you need to go, you just mark an arrow like that, and that's your position vector R. And if you move by some distance, let's say R prime in this way, or let's rather go this way, R prime vector, then your displacement is measured like this. And this is going to be, let's say, dl, all right? And if this is our origin, then we can simply write our position vector R as x cap plus y cap plus z cap, where x cap, y cap, z cap are the unit vectors in our Cartesian, in our coordinate system that we've taken. And our displacement dl is going to be a displacement in the x direction times x cap, the y direction times y cap, and in the z direction times z cap. Now, what this tells you is that your total displacement is a vector sum of your displacement in every individual direction that you move in. And in case your point here is not at the origin, then you can simply write dl is equal to r minus r prime. This is something that comes in handy when you're doing electrostatics and so on. It's not that important. The next we move on is to gradients. But before that, let me just do a little bit of partial derivatives. I'm sure all of you here are already familiar with ordinary derivatives, but we'll just do a quick recap of partial derivatives. Now, let's say you have a function f, which is a function of more than one variable. So here in this case, let's take a function that depends on x and y the same. And an example we'll take is sine of xy. So you might be familiar already with just sine x or just sine y, but now we're taking a function that depends on both x and y. A partial derivative is defined as follows. Quite simply, it's denoted as this fancy d. Some people call it del, some people call it do, but I prefer calling it do, from the Play-Doh, if you remember from your childhood. Do f over do x and do f over do y. Now, what this simply means is that when you're differentiating f, you're differentiating it only with respect to x, and you keep y constant. This implies y is constant. And by convention, by extension, when you're doing do f by do y, it means you're differentiating the function f with respect to y, and you're assuming that x is a constant. So if you go back to this example here, if this is our f of x comma y, do f by do x, do f by do x would just mean do by do x of sine xy. Now, what this means here is that I only differentiate with respect to x and treat y as a constant. The derivative of sine is cos. So I'm just going to write it as cos of xy. And now I differentiate the internals of it by chain rule. And if I do that, my y is a constant, so that just comes out. And do x by do x is just 1. So I'm not going to write that. Similarly, if I was to do this, do f by do y, I treat x as a constant now. And if I was to do that, I get x times cos xy. So that's a quick introduction to partial derivatives. Now, what this geometrically means is that you're moving in one direction, keeping the other direction constant. And this idea becomes a little more clear when we do gradient. By using partial derivatives, you can define your total or ordinary derivatives as follows. Your ordinary derivatives, let's say df, can be defined as do f over do x times dx plus do f over do y times dy. Now, what this just tells you in rough is that the total change in f, this is the total change in f, is equal to the change in the x direction. This is the change in x direction plus the total change in y direction. That's about it. It's very similar to our definition here of dl, right? But it's just been extended to more variables. So this falls under the realm of multivariable calculus. All right. So the next thing that we'll head into is the gradient. You might have already seen definitions of how the gradient is defined. So I'm going to write it in a form that you already know. For a function t, you write it as do t over do x times dx plus do t over do y times dy plus do t over do z dz. All right. Now, what this just tells you is, again, like we discussed in the previous example here, df is equal to the change in x and the change in y. Here, it extends the idea to 3 dimensions. You have x, y, and z, and it just tells you that about the change in each direction. Right. Now, you might argue that, from your previous experience, you would know that this so-called gradient quantity is a vector quantity. So I'm not quite justified in writing it like this, but what this represents from our previous discussion is actually dt. That gives me the total change in this function t, which is a function of 3 variables. All right. But now let's say we want to understand it in terms of this dl quantity that we studied before, dx x cap, dy y cap, dz z cap, z cap. Right. So that tells us about how it changes in each direction vectorically. You have a sense of direction now. And in order to do that, you can, you define something called the del operator as follows. D by do x x cap plus do by do y y cap plus do by do z z cap. Now you see, you might be tempted to directly tell that this particular operator called the del operator, we call this the del operator, right, is a vector quantity, right? You might want to put it as an arrow like this. It's fine to call it that, but it is not a vector. All right, so I'm going to put that in a red color here. This is not a vector. You just work with it as if it were a vector, but it's more of an operator. This operator term is the key here. All right, so by itself it is useless, but it makes sense only if you apply a function to it. And so using this, we can define our dt to be grad of t dot dl vector, where dl from our previous discussion was dx x cap plus dy y cap plus dz z cap. Now you see, if I was to take a dot product, I would just get back my initial expression, which I'll call equation 1. I'll call this equation 2. So with this, we define gradient of t to be equal to dou t over dou x cap plus dou t over dou y cap plus dou t over dou z cap. This is how a gradient is defined. And clearly, this is a vector quantity. I'm sorry, was there a question?
Yeah, my question is, means this del operator is not a vector, is just kind of operator, and
It's
grade
just a
of
vector.
t is,
Yeah.
and grade of t is a vector. Means when we operate on some scalar function, then it will form a vector.
Exactly. Yes. So yeah, thanks for mentioning that. I missed that. T here is always has to be a scalar function. And what a scalar function means is that it has a unique value at every point. All right. And why do we need it to be a scalar function is a matter of you doing your self study. So I'm not going to get into that due to the time constraints, obviously. Now we'll move on to how else can we understand this del operator, right? So with the del operator, you can perform your vector operations normally, the dot product, the cross product, and so on. So we'll assume a vector function. Assume a vector function. We usually take this to be f, so I'm going to write it as f arrow. Now we define a quantity called the divergence, all right, which tells you about the spread. So divergence tells you about the spread of f, the field that you have. And this will become more intuitive and a bit more visual when we do electric fields and magnetic fields in the future. So the way this is defined is del dot f. All right. Now I will be omitting the arrow sign on top of the del operator because it's an operator and not a vector. Although you are free to put it like this, it still means the same. It doesn't make a huge difference, right? But for, I am used to not putting the arrow with a del operator, so I'm not going to do that. And the way this is defined, as you might expect any dot product to be, if this vector, let's say, has components fx, fy, and fz, it has some value at every point, x, y, z values at every point in space. Then the divergence is defined as dou fx by dou x plus dou fy by dou y plus dou fz over dou z. And you can see that this is a scalar quantity, as you would expect it to be, because a dot product is supposed to give you a scalar quantity. Why should it give you a scalar quantity is again a topic of study, which you are free to go ahead and study it on your own. So yeah, divergence sort of tells you about the spread of things. So if I was to have, let's say, a vector field like this, so on, and if this was my vector field f, then computing the divergence would tell me how much is this field spreading out. Is it like an inverse relation or something like that? Right? It tells me about the sources and the sinks. So if you were to assume that this is a positive charge or something, then this would be your electric field lines and so on and so forth. But I don't want to complicate it for you at the very first stage. Right? The next thing we'll go into is called the curl. So I'm going to get rid of this diagram here. It's not necessary. The next thing that we're going to look at is the curl. Now, curl, as the name suggests, it's like a very obvious way of looking at it. Curl is about how much it curls up, right? So if you've observed, let's say, a sink of water that has been stopped, and then you just let it go, you see whirlpools that form and it goes in like that. Right? Oh, whirlpools are the best example if you've seen images of them. Right? This example for that is Whirlpool and not the machine company. All right. So it tells you about how much F curls, and it literally is about the curling of the whole thing. Right. And the way you write it is del cross F, and it's defined as follows. Del F. Okay, let me not write it like this. It's a long form. So we can rather put it in the determinant form of curl of cross products that we've learned. So in a Cartesian system, we have x cap, y cap, and z cap. That's our basis vectors in Cartesian system. And then we learned that we are supposed to put the components of the first vector. So this is why we assume we work with the del operator as if it's a vector, right? We sort of play around with it loosely. And we can write its components out here, which is dou by dou x, dou by dou y, and dou by dou z. And now we have the f vector. The components are fx, fy, and fz. And we take a determinant of the whole thing. Now, one thing that people tend to mess up is that you are not multiplying this component. So I'll just work out one component of this determinant. So I'm sure all of you are already aware of how to compute determinants. I'm assuming that, and I'm moving ahead. So if you're computing x cap, you remove the row and the column, the respective row and the column, and you compute dou by dou y fz minus dou by dou z fy. What this means is you're not multiplying dou by dou y and you're not multiplying dou by dou z in fy. Right? What it essentially means is that you're operating them. Right? So let me put it in red and a small line, perhaps. This red arrows stand for operating, not multiplying. All right. This is something that even people at master's level sometimes tend to mess up with. It is not multiplying, but you're operating on it. Right. And I will leave it to you to work out a few exercises from let's say Griffith's textbook on electrodynamics. All right, so that's about it for how you work with the del operator. I will leave you with the properties of the del operator. There are several product rules. I'll just mention a few, and I will leave the rest to you to explore. The most simple ones are as follows. If you're taking a gradient of, let's say, two functions, the sum of two functions or difference of two functions, it's just gradient of f plus or minus gradient of g. It's as simple as that. Right? Similarly, if you're taking the divergence of two vector functions now, a plus b, then it's simply going to be the divergence of their individual. It's going to be the sum or difference of their individual divergences. There. And similarly for curl, if you're taking curl of the sum or difference of two vector functions, it's just going to be the sum or difference of the individual curls. Now I will leave it to you to explore the rest. All right. So here f and g are scalar functions, which means they are independent of direction. And a and b are vector functions. Yeah, so that's about it. And we'll just look at three theorems that are vital in order to convert one form to the other, and I'll conclude with that. So the first theorem that we're going to look at, these are called the integral theorems. I think we can just stop at two theorems, so shouldn't be a problem. So the first one we're going to look at is the fundamental theorem for gradients. Okay. we saw how we define our gradient to be. So I'm just going to go ahead and give you what the theorem is. And it's very similar to what you learn in your first class of integral calculus. It's very similar to the fundamental theorem of integral calculus. All it says is that the integral of gradient of a scalar function dot dl, because that's how we defined our total derivative to be, is from 2 points A to B, is simply t of B minus t of A. And of course, these will be, yeah, let's just leave it at that. All right. What this tells you is sort of that your integral, we call this a line integral. All right. It depends on the path you take when you're computing your gradient. So there are several paths that you can take when you're computing your gradient. And if you work it out a little bit, you will realize that this is, although it looks as if your final result depends on the endpoints, the path that you take eventually, even though it's non-intuitive, it would be independent if it was a closed loop, right? So if for a closed loop, A equal to B, right? If you have something like this, for example, if it's a closed loop, then your A would equal to B, and you get a closed loop. So what happens then is T of B is equal to T of A, and that would imply that your entire integral grad T dot dl from A to B, which you can represent as a closed integral as follows. I keep writing divergence. Dot dl is just equal to 0. All right. Griffiths gives a very good explanation about this, so I urge you to go ahead with that. Now that we've done the fundamental, yeah, sorry, was there a question?
Yeah, my question is, means it is depend on the final and initial point. Means we can say that this is a conservative field.
It depends on what T you take.
Okay, can you elaborate?
There is another condition for it to be called a conservative field. All right, you can't directly conclude from this that it's going to be a conservative field, because there is one more condition that it must satisfy, and that I'll get to that in the third theorem that I'll be doing right now. Right?
Okay.
Yeah, you are almost there, but it just needs to satisfy another condition. Right? So we'll get to that. Not to worry. Okay. All right. The second theorem that we're going to do is the fundamental theorem for divergence. This is also sometimes called the Gauss's divergence theorem, or sometimes just divergence theorem. It's your wish as to what you want to call it. Now, what this tells, briefly, is the integral of now you remember that these need to be vector fields. So I'm going to call this vector field V, just because V stands for vector. It's a little easier to write. All right, times dV is equal to the closed integral V dot dA. And this is taken over a volume V, and this is taken over a surface S. Right? Now, what this tells me, now, since we have divergence and so on, it is obvious that we are in the realm of 3 dimensions right now. Right? So what this tells me is that if I have a surface, let's say some region of space which has some volume V, and this surface is, let's call it S, all right, and there's a vector field that is defined in this. Now, what this divergence and so on tells me is that the sources or sinks that are there, Griffith calls it faucets, all right. And if I'm wrong, I'll be more than happy if someone corrects me if I get wrong somewhere, right? But what this tells is that the entire faucets, the sources or the sinks, right? So the integral of faucets is equal to the closed integral of flow through the surface. Now, I will try to demonstrate visually as to what it exactly means. So if you have a vector field, You remember the diagram that I had drawn? If you have a point source here and the field lines sort of spread out from here, and divergence is a measure of this spread, right? Now at the edge, if you keep following one of these, it flows out the surface. If you keep following this, it flows out the surface like so, right? So the right-hand side of my theorem here tells me about the flow through the surface, whereas the left-hand side tells me about the field inside the region of space that I'm considering as in 3 dimensions, right? So that's about it. There's good exercises in Griffiths that you can work out and verify this theorem as to why does it have to stand. But this is the rough idea of why exactly is this there. Right? And one more point that I'd like to mention is that this theorem here, on the left-hand side, this is actually a triple integral. And why is it a triple integral? Is because your volume element, if I was to consider a small volume element here with some volume dv, then it's actually equal to dx times dy times dz. And so if I was to actually write this theorem in its full form, it's going to be triple integral over the entire volume V, divergence of V, dx, dy, dz. All right, and this again on the right hand side, it's an area. This is called an area element. So if I was to consider some amount of area over here, then my dA would be some normal to that area component. It might get a little too complicated. It's totally fine. All you need to understand is what this means as a whole. All right, and so the right hand side tells me that it's a closed surface integral over the entire surface, and it's going to be V, the vector field, times roughly, I'll just write it as dx dy. So it's a double integral, right? So what this divergence theorem helps us is to convert a triple integral or a volume integral to a surface integral. So you kind of have a relation between volumes and areas over here. You can try to measure as to what is the relation. If I was to have a vector field, let's say in my room, how would it affect the surroundings outside my room, for example? Now this takes us to our last topic of the day, which is the fundamental theorem for curls. The fundamental theorem for curls. Right. Now this again has a very similar statement. All it says is that this is also called sometimes the Stokes theorem, which some of you might be familiar with. Okay. So what it says is the surface integral of curl of a vector field V dot dA, because it's a surface integral, is equal to the closed line integral of that vector field taken over a perimeter P. All right. Now, curl is a measure of, okay, so let's draw a surface again, some random surface. All right. Now we'll assume this to be a 2-dimensional surface because area can be represented in just 2 terms. So here we have dA to be equal to dx dy, and our line element dl, we can just write it as dx x cap plus dy y cap, and so on. Right. So what this tells is, if I have, I'm going to use blue again. If I have something here which is curling, right? If I have a vector field that curls like this, what is the net effect on the surface? So what the right hand side is telling us is about this on the surface itself, on the perimeter of the surface. How would that behave? An example that I can give you for this is if you were to, if you have a bucket of water and you start swirling the water inside it, and if you spin it hard enough, the bucket itself starts to rotate if you give it enough energy. Right, so what's happening there is the water inside that is swirling around, that is forming a curl, a whirlpool, is transferring all of its curl to the perimeter of the bucket. And so eventually, with enough energy that you give, the bucket also starts to rotate a little bit. That's what the Stokes theorem is all about. So in other terms, we call this right-hand side to be the circulation. of the vector field V. And this just tells you about how it behaves inside your area, the curl. It's again, like we saw, it's just about the measure of how the field behaves inside. So that almost brings me to the end of all that I wanted to discuss today. I'm really sorry it was a huge mess initially. Coming back to the question that one of you had about conservative fields, I urge you to look at this theorem called the Helmholtz theorem, and I'll just give you a brief of what it is. So if Helmholtz theorem, and then again applied to potentials and so on. So what it says, if you have a vector field F, all right, and if curl of F, right, curl of F vanishes, right, if curl of F is 0, then you can express F as the negative gradient of a scalar function. We'll just call it F, right? So what this tells me is that if curl of F is equal to 0, that implies that F can be represented as negative gradient of some scalar function F. Why negative? That's just convention. That's just something we've been following all along. All right. But again, if you can express your vector field as a negative gradient of some scalar function, then that would imply that the curl of F is 0. And if these conditions are satisfied, only then do you call F to be a conservative field. All right. And small f is called the scalar potential. All right. So if we go back to our problem here, T here acts as the scalar potential, but the condition that it must satisfy is that it's, it must be the negative gradient of some other vector function. Only then can you say that this T is the scalar potential. So I hope that answers the question that one of you had initially.
Yeah, I have one more doubt. Here, when we see that curl of F is equal to 0, means what? There is no normal component along the surface, which means the force is acting, means the field is acting. Okay, means we can say that this means the component these are in the plane.
Yeah, but I would urge you to look at it in a simpler perspective, right? The component wise, yes, you can compress it down to a plane, but what this simply means is that if you have a vector field, so I think the diagram is still here of the curl. Did I draw a diagram for curl? Okay, no, maybe not. Okay, so what this just tells is that this entire curl component that is there, this curl of a vector field that you're trying to measure, there is no rotation happening. That's like the simplest way to look at it. Right, you don't even have to get into the normal components and see how it behaves and so on. If the curl is 0, then it doesn't rotate. That's it. And if it doesn't rotate, then that means there is some scalar thing that's happening, which you define it to be the scalar potential.
Okay.
Right. So this is one thing that I would like to urge is try not to complicate things too much. Right. One of my professors always tells me, keep it simple. It's never too complicated unless you decide to make it complicated. So you can look at this in terms of components and so on, because I said that the curl gives you a normal component perpendicular to the plane containing the two vectors that you're crossing, right? But another simpler way to look at it is just that there is no rotation. Now, why do you call gravitational field to be a conservative field? Is because if you have a surface, right, your gravitational field just acts like this, right? In other terms, you see that it's not curling around like this, right? The gravitational field doesn't curl along like this. It doesn't go like that. It's just straight lines pointing towards the center. Does that make sense? Right? They're all just eventually just pointing towards the center radii. That's it.
Yeah, means we can say that if this is if plane is not rotating, means we can say that its kinetic energy is zero. In the physical way, we can say it has only a potential and associated with it.
Sort of, yeah, yeah. So this scalar potential, what you get is an equipotential surface. That's how we call it, right? This F field that you get is called an equipotential surface, right? So what this gives you, if you look at it in terms of surfaces, this gives you an equipotential surface, and that is why we say that it depends on the potential energy, or in other terms, it only depends on the initial and the final position of the particle in a conservative field, right? This is why we say it, because any conservative field that you have, and if you're claiming that the energy of the particle is purely potential and that it only depends on the initial and final positions, then it implies that the curl of that particular field that you're talking about is going to be zero. The corresponding vector field is zero curl, has zero curl. All right.
Yeah, thank you.
No problem. All right. So I have a small thinking experiment or thinking assignment for you guys. So I said that if curl of F is zero, then you get let's say what do we call it? Non-zero curl field, right? I want you to think what happens if the gradient of a vector field is zero. What do you get then? What does it imply? Right? This is a small thinking assignment. You don't have to turn in answers or anything of that sort. You can just leave a message in the gamma ray or the neutrino channel or in the lounge, wherever you feel fit. All right. It's just something to think about when you go about this. All right. And I'll just give you a hint. It's very similar. So we know that if curl of F is zero, we can represent it as the negative gradient of a scalar function. Oh, sorry, I called it F. Right? So what about when the divergence of F is zero? Can you do this? Is this possible? Or, is there something like that? That's something that I leave for you to explore. And with that, I conclude today's session. I'm really sorry about the mess that happened initially. I wasn't really expecting that. So yeah, any questions? I'm open to them. Let me see chat box if there's any. Okay. It's not a constant field. Stephen, it's not going to be a constant field. Think about it. Because that is one of the vital things that we require for electromagnetic fields, right? So that's something that we're going to pick up from tomorrow. And Tane, what's going to be taught tomorrow is Maxwell's equations. So yeah, I was coming to that. I didn't want to tell it right away. I was waiting for a few questions. But since it's come up, tomorrow we're going to be discussing about Maxwell's equations. So again, I would urge you all to go through simplest resources that you find on Wikipedia or something, or even the book on electrodynamics by Griffiths. Just go through the chapter on, I think it's called electrodynamics, chapter 7, I believe it is. You need not understand it entirely. Okay, when does del F become zero? Well, it just means, no, I don't want to spoil it, but think about it in terms of, yeah, so the answer is there. Arata has given the answer, divergence-less fields. So when you don't have divergence, your del F becomes zero because your vector function F is not spreading out or something. But here comes the question again, right? What happens if it's not spreading out? Right? That's the question that I have for you guys. So think about it. Yeah.
Yeah, I would like to answer the first one. I think it is not spreading means it's kind of a static thing. So like for magnet also, if we cut the magnet, then it will also give you a south pole and north pole. Just
South Pole and North Pole are arbitrary points that you define. Right? You just choose to call one point north and one point south. So there is really no distinction between that. And the magnetic field, if you look at it, if you've seen experiments, where, they throw iron filings at a magnet and it sort of arranges themselves into something, closed loops, right? If you've seen those images, those are not static, right? They move, which again we will see in tomorrow's discussion on Maxwell's equations. The field lines will be closed loops. Well, yes. I'll just tell you yes, but how would you represent it mathematically? Magnetic field is divergence-less. Yes, that's an example of why, when the divergence of a vector field is zero. But my question is, what does it imply? Right? What's the consequences you have because of it? All right. Vaishak is sort of close to the answer. The field lines will be closed loops. Yes. But what would it imply? How would you represent it mathematically, and what would you call it? Is where I'm pointing towards. Okay, is there any other question that I missed out? I'm really sorry if I did. But okay, I don't think I've missed out any question. All right. The fields are not piercing out or into the volume. Explore that out. Explore that out.
yeah, or we can say that there is no loss of the field, means incoming is equal to outcoming. All incoming is equal to outcoming field.
Can you really say that? So you are telling me that if I was to go very far away from a magnet, I can still feel the magnetic field?
No, not at left. Means this field is decreasing, of course, if you go away from the magnet.
So let's not worry about strengths here. Okay, let's not worry about the strength, because ideally I can assume this to have infinite strength. Right? Mathematics doesn't restrict me from having fields that will fall off at a distance. I can just say my vector. I can just define my vector field to be something that has the same strength even at infinity. What then? Okay, so we have a thing here. Aruna is saying, but they can still have curl. And yes, Paratha has answered, of course, yes. There will be curl. Yes, correct. So the answer is almost there.
Doesn't it mean flux is zero? Net flux?
The net flux. Yeah, sort of. If by net flux you mean the flux going in and out, then yes, it'll be balanced. Stuff that goes out would equally enter from the other side. Right? These are the ideas that we'll try to discuss in tomorrow's discussion of Maxwell's equations, because they sort of manifest themselves into the electric and magnetic fields, and we'll understand all of these ideas that you guys are telling about in the chat box with the electric and magnetic fields. So that's something that we already know, and it would help us understand it a bit better. There will be curl. Yes, there will be curl. But how would you represent the curl, and what would the implications of the curl be? Is again my question. F will be a curl of some other vector function. Very good, very good. What would you call that vector function? Here I was able to call it as the scalar potential, or something that it gives rise to be the equipotential surface, any one of those. What would you call that vector function to be? Right? Guys, don't spoil it. Take some time to think about it. All right. Think about everything that you can do with that vector function. As Rajat has told, F will be the curl of some other vector function. Yes, that is the answer. So I'll give it to you. But what would it imply? Right? What would it imply for F, and what kind of restrictions would you have on A, if you would have any restriction on A? Right. And what if you had a field that is like a mix of everything, right? If you had a field that has like zero curl at some point, and will the gradient be zero? No, it won't be zero. Or maybe it can. Let me not tell anything definitively. I don't want to spoil the fun. Aratha agrees with me. Spoiling will kill the interest.
If the curl is 0, doesn't it mean that the field is irrotational?
Yes, exactly. Oh, that's the word I was looking for. Thank you very much. So here, this is. I hope my screen is still shared. Yeah.
Yeah, it's shared.
This F is irrotational. And as someone already pointed out, if the divergence is 0, then this is a solenoidal. But those are just names that you give to fields of your choice, right? That just tells you how the field, how F is, right? But it doesn't tell you what it implies, right? So, yeah. All right. Are there any other questions I can try and answer? Otherwise, I'm way past my time that I said I would take. So, yeah. Tomorrow, I'll make sure I join in a little early and make sure there's no other glitches that happen, and we can start off at the prescribed time of 7:30. All right. So feel free to reach out on the Discord channels, either the lounge or the Gamma Ray thing. And if there are people from the neutrino group here, you are again welcome to join the discussion on Maxwell's equations tomorrow. Like I said, it's a collaborative thing, so you're free to gain knowledge from every single point. Thank you, Aratha. I hope I'm happy I could entertain.
Can we add to the discussion of Maxwell equation tomorrow? At what time?
It's going to be at 7:30. That's when the usual Gamma Ray meeting is. So
Okay.
we're going to start the discussion at 7:30. So you guys can plan your neutrino accordingly. Sagar, I hope you can take care of that.
Yeah, I'm from neutrino group. That's why I'm just saying.
I realize. So we can sort of push it by 5-10 minutes to wait for you guys to come in.
Okay. Yeah. Thank you.
Yeah, no problem. You're welcome. Alan, yes, we do have 6 weeks for a lot of interesting discussions like this. So, yeah. Yeah. Been on screen since 9. And I've been on screen since 8, so I totally get it. Thank you, Ashura. Glad you enjoyed.
Hi, this is Aruna.
Go ahead. Yes, Aruna.
Yeah. Actually, I just finished high school, so will I be able to understand this?
Yes, absolutely. I will. So it's totally no problem if you haven't understood, more than 50% of what I did today. It's totally fine. All this is sort of tools for you to realize what is going on in, let's say, scientific papers and something. But what I want you to focus on is where I talked about what they imply, right? Like this figure on gravitational field that I drew here, a very bad figure, but right. I just want you to understand the essence of it. I don't want you to, it's not important for us to make sure you understand the high level math, right? It would be great if you did work on it, obviously, but if you don't push it. All right. Don't burn yourself out and be like, oh, I'm not getting this, so I don't know if I can participate or not. Don't worry about that at all. All right.
Yeah.
Just focus on conceptual understanding as much as you can.
Yeah. Thank you.
Yeah. No problem. No problem. And if you have at any point any questions, feel free to reach out to us. All right. The mentors, the admins, your peers, everyone is here to help you out.
Vikrant, I'd like to add one point.
Sure, yeah, go ahead.
Tomorrow at 6:15 p.m. We'll be doing a presentation on particle and astroparticle physics.
Okay.
If anyone is interested, even from Gamma groups can join. It will be on Zoom.
Absolutely. So any sessions that happen in the Neutrino Discord server or in the Gamma Ray Discord server or even on Zoom, both the teams are free to join in, right? If you want to just learn, you are free to join in, right? There is no restrictions at all. You're not going to be removed from a meeting just because you don't belong to that group. There's nothing like that of that sort, all right? So don't feel afraid if you want to just pop in and give some advice, give some suggestions, have a discussion, ask some questions. You're all free to do that. No restrictions at all. Okay, so if that's done, someone told me this in high school, maybe I can pass one sem easily in UG. Oh, you can pass all semesters in UG. Don't worry about that, Anshul. All right, so we can wrap it up here for today. Thank you for joining in. I hope you had fun learning vectors and vector calculus. Other hosts here, Jivan, Hardik, and Ashwin.
Yeah, can you hear my voice? I was not able to unmute.
Okay.
Hello.
Yeah, we can hear you, Hardik. Go ahead.
Okay. Yeah. So thank you for joining. Tomorrow we'll see you, I guess, in 6:15 because of the Sagar's presentation, and from 7:30 to 8:30, Vikrant will teach the Maxwell's equation again. Overview.
Oh, wait. A correction. I'm not teaching Maxwell's equation. We're going to have
Yeah.
a discussion. So all of you, please do go ahead and read up on Maxwell's equations from Wikipedia or something.
I've shared resources, so you can have a look at that also.
Shivalik, my SGC papers weren't easy. All right, my first semester score was like 70%. So, and my first semester master score is again 70%. So, yeah. The term easy is relative, as all of you would agree. So let's not rather get into that. But yes, I do wish all of you all the best for your upcoming exams if you have any. And yeah, this project we'll try to make it as fun as possible for you, all of you guys, so that everyone can benefit and walks out with understanding the basics as much as possible.
Great. Then. Good night.
All
everyone.
right, so it's been a long day for everyone. Thank you for joining in, and I'll see you all tomorrow.